Okay, welcome. We'll start. So welcome to the second session of the restoration and rehabilitation of desert ecosystem. The first session was in the morning, and the first session concentrated on population level, so mostly reintroducing species to desert environment and everything it entails, both...
Ladies and gentlemen, the event is about to begin.
We are about to begin. So we're introducing species to desert environment, both for the species' sake, for conservation sake, and for to return ecosystem function to desert ecosystems. It's also known or remembered as the best session in DDD history so far. And now we're continuing the session, looking at a wider scale, going to the ecosystem scale, the rehabilitation of the ecosystem, of desert ecosystems. And our first speakers come all the way from Northern Arizona University in Flagstaff, Matthew Bowker. And he'll talk to us about establishing biocrust to rehabilitate drylands, some obstacles and possible path forward. Matthew, thank you for coming.
Thank you, Oded, for the invitation and the introduction. Thanks to all of you for coming. Can you hear me? Thanks for coming. I'm going to talk today about some of the challenges we face when we're trying to restore biocrusts and some ideas for getting past those challenges. So biocrust is a shortened version of the phrase biological soil crust. And there's some images here of what those look like. You can find them in the Negev, and you can find them in many places in the world. And what it is kind of a living skin on the soil surface that's created by the organisms, and they are generating a very thin aggregate just on the soil surface. Okay? They are engineered by various organisms, including microbes like cyanobacteria, but then also small plants and other organisms like mosses and lichens in really any combination. They're very interesting, but they're also extremely important to the function of dryland ecosystems, and that's for various reasons. One reason is that they are photosynthetic and they harbor nitrogen fixers. So when you have a biological soil crust or biocrust, that means you are adding and accumulating soil fertility. They're also very influential in hydrology. They can influence the infiltration and runoff balance, the capture of non-rainfall water, and also soil water retention. Perhaps their most characteristic function is aggregating soil and thereby protecting against erosion. And then finally, they're also strong interactors with other biota. They can really shape microbial communities and kind of steer plant community development one way or another. So in my group, in this research program, our overarching goal is to use these communities to rehabilitate degraded water-limited ecosystems. And the first step in this process is to grow biocrusts on demand. And we have a few ways of doing this. We do it in a few different systems in greenhouses. These are some of our greenhouse methods here. And we've also been experimenting with outdoor farms, like little farms, to grow biocrusts. And I don't want to focus on the growing part today. I want to focus on putting them into the environment. But I will tell you about one of our growing systems. It's a fog culture system. So we've created a fog chamber in our greenhouse, and what we have is a piece of cloth here, and these are mosses from biocrusts, and they're being hydrated just from the constantly precipitating atmosphere and growing. And then about 8 weeks later, it looks like this, and we've got basically a kind of a moss carpet, about 1/2 centimeter thick, and this is material that we might want to put into the field. This system is really nice because there's no soil, therefore it's extremely lightweight, and that enables us to vertically stack growing surfaces. This is 10 high. All we have to do is move them around once in a while. to ensure that there's even light. So that's the first step, growing biocrusts. And where we want to get to is establishing them in the field. So going to degraded field sites and seeding them, so to speak. And that is easier to say than it is to do because the world is harsh. There's many obstacles out there. The environmental parameters may be harsh, the climate, or could be something wrong with the soil. The organisms that we grow, sometimes they seem to lose field hardiness because we grew them in a nice environment. And then we also see a lot of loss to wind, water, and even insects. Sometimes when we go back to check on the biocrust material that we put out, it's no longer there. And we don't know, did it die, or is it having a happy life somewhere else? We can't tell. So, given all these obstacles, what we'd like to do is we'd like to think of possible solutions, ways to get around these obstacles, or at least minimize them, diminish them. So that's how I'm going to structure my talk. I want to talk about 3 possible paths forward to get past these obstacles. And the first idea is using phytohormones or osmoprotectants to improve the field hardiness of the biocrust material that we grow before we introduce it into the environment. And here I'm asking the question, can adding a chemical or altering our method of production induce a more hardened material, more field-ready material? And the first chemical I'm going to talk about is just sugar, regular sugar, cane sugar. This might seem sort of weird. Why would you add sugar to biocrusts? And that's because in desiccation-tolerant moss biocrusts and mosses, the sugar is sort of a placeholder for the water when the organisms dry out. These organisms dry out regularly. And this prevents damage to the membrane and keeps the organism intact. And it's also an energy source for repair, and because it's a solute, it has antifreeze properties as well. The other chemical is abscisic acid, and you may be familiar with this as a phytohormone. In mosses, what it does is it activates drought and desiccation tolerance mechanisms. So it prepares them for the desiccating environment that's coming. In this experiment I'm about to show you, we also produced moss 3 ways. So we just took the moss component from the biocrust, we cultivated in that fog system I showed you earlier in the greenhouse, and then we did more of an outdoor grow with 2 kinds of irrigation strategy. One was just passive, whatever rain and snow that was received at the farm in the winter. And the other one was allowed to continue growing into the spring with supplemental irrigation, okay? So this is our system, and all 3 kinds of moss were added with sucrose or ABA, abscisic acid, or neither. And this is what we saw. So on this axis, this is how much of the moss is still there when we checked on it 1 year later. Okay, so 1 would be 100%. And you can see that they're losing ground. Okay, but the first pattern you can see has to do with the growing method, which is indicated by the colors here. And it's very easy to see, especially in this time period, that the outdoor cultivated moss with no supplemental irrigation was greatly outperforming the other types. Okay, so it seems to be more hardy. A little more subtle, harder to see with the eyes, but it came out in our statistics, is that abscisic acid boosted establishment a little bit by like 10 to 15%. And you can see that when you compare, for example, this bar back to the control and this bar back to the control. Okay. It's more pronounced in some moss types than others, but there's an overall effect as well. I should point out now this caveat over here. After 3 years, all the mosses were dead. So we did not achieve long-term success, but there's enough that's suggestive and exciting here to tell me we should keep looking at this, and maybe we can get a better result in the future. Okay, another idea to solve various problems is attaching biocrusts to cloth. And if you did this, you could decrease loss to wind and water erosion. You, depending on how you used it, you could buffer the environment. And depending on what the cloth is, you could reduce weed competition from exotic plants, for example. So going back to the fog culture system, it is a production method, and it does generate new growth of mosses, so that's great. We can take some moss and turn it into more moss. But also very important is the process of doing that attaches it to cloth, which is very convenient and an interesting thing to play with. So we did a field test of our moss cloth material, and this is growing on burlap, like sackcloth. So we took some pieces, we applied them to the soil with the moss up. We applied them with the moss facing down underneath the cloth. To separate out the effect of being attached to cloth, we also scraped some mosses off of cloth and added them loosely. And then for a comparison to what the local moss would do, we gathered some local moss and scattered it loosely in some plots. So this is our comparison we're making here. And here's some of the results. So this is just moss cover, not percentage of the original added, just cover. And you can see they started off pretty high cover. Our cloths were pretty mossy. And then this is shortly after we set up the experiment. Then going into our first pretty severe summer drought, we saw a massive drop-off, dieback. And it does seem to be that some treatments are doing better than others. But that's just kind of a window into the future, because after the next winter growing season, the next spring, we saw a really strong rebound. And in particular, it was these ones that are cultivated on cloth, and especially the cloth with the moss underneath it that established really well. So this is what that looks like. So after a year, we made a high moss cover patch with a piece of cloth over it that will eventually rot. And we think this worked because our moss is held in place by the cloth, and it's also buffered against drought because we've created a moist microsite that retains water and provides shade. So this makes us wonder, what else can we attach moss to in a fog chamber? So we've been thinking a lot about weed cloths, because exotic invasive weeds are a big problem at one of our major study sites. You have to fight the weeds if you're going to do restoration. So we've been investigating putting moss onto these, and we're looking at 5 different materials. Because we had so much fun with burlap, we kept that one. We know this is a poor weed barrier, but it's a great moss facilitator. Where we do our work, MPG Ranch, they use a lot of synthetic weed cloth, so we tried that one. And then there are various biodegradable weed cloths that we've given these fun nicknames, corn, paper, and trash bag, based on their appearance and some of their ingredients, and grown moss on those. So these results are very preliminary, and we did moss side down cloths and moss side up cloths, so we kept that part of the experiment. And I can only tell you what's going on the face up ones because we can't see what's underneath most of these. But what we can see after 6 months is that some of the fabrics are not retaining very much moss, but some are. And of the biodegradable materials, it looks like the corn is promising. It's not quite as good as the burlap, but it's pretty good compared to some of the others. And after 12 months, we can still see that these organic cloths, they are starting to degrade, but they are still keeping weeds out, so they're still doing that part of the job. So it'll be next spring when we can go peel them up and see if the moss is still there and see if we kept out the weeds. So, we're not crazy people. We know that you can't cover a landscape in cloth. So how would we use this? We need to use it in small areas strategically to have a bigger effect, right? So some of our ideas, based on where we're doing our work, are using the moss burlap to stabilize like erosion problem sites. And there are a lot of these south-facing slopes in that study site where either nothing grows or only exotic weeds grow. And you have to sort of choose your poison. Instead, we want mosses and shrubs. So if we could stabilize that, we may be able to facilitate a future shrub planting because shrub plantings tend to fail in these sites. Another idea, use squares of weed cloth like this. Clear the weeds, use the weed cloth to suppress the weeds, thank you, and facilitate a shrub planting, eliminate the competition. And then idea 3 is using pieces of our moss burlap to facilitate seeding by seeding grasses and forbs underneath the cloth and helping to diversify a partially restored site. Okay, the last one I want to talk about is pelletization. If you put biocrust into pellets, you might decrease loss to wind and water, you may buffer the environment, and this is a product you could broadly disperse instead of just using in small areas. Basically, what this is like is we're making pasta almost, but it's instead of putting basil or something in it, we're putting moss into a clay-based batter, rolling out some noodles, and then reshaping them for experiments. And we're interested in different recipes, shapes, sizes. This is what our first field trial looked like. This is the day we set it up. And after 6 months, I can tell you that combinations of the pellet size and shape are very influential. You can see that the large round pellets are underperforming compared to some of the other combinations. And there was also, we did 2 different recipes too. One has pectin in it and one does not. And you can see that especially over here when we're looking at moss stem counts, that recipe 1 was better than recipe 2. That's a moss ball after 1 year, by the way, or moss pellet. So our approach is to think about what obstacles we may face, and then we try to have a solution in our back pocket for each of those obstacles. And there's a million things to do. This is an open field for research, and there are many creative combinations of these things and variations on these themes that remain to be tried. And I'm confident that we can start to see some real success if we keep trying new things. Thank you for your time.
Thanks a lot. And we have time for some questions. Yes.
Thank you very much for the interesting talk. I was wondering, when you use that burner, did you have any problems with termites heating it up within a very short time and then pretty much turn the scot, or with any other organic material that you use?
No, we haven't seen that. I imagine that we might in some of the sites where we work that have more termites, but maybe this site doesn't have them. I don't know.
I have a question. You covered a lot of the results that putting the moss face down.
Yes.
As you made it, put it face smaller interaction with metal damage to soil culture, because it seems the initial conditions were going faster. So do you consider a stage where you're going to design a field which you had with the moss and like as management conditions would like?
I'm not sure I caught everything that you said, but are you saying maybe the effect of the moss is more contact with the soil microbes?
For example, because it's another interpretation of the same result, which is consistent with how the initial conditions affect its success later on in actions.
It could be. We work in a very there's a research exclosure that's normally kept plant-free where experiments are done. So it has a very low microbial biomass, a very depauperate microbial community. So maybe it is, maybe it isn't. But it'd be interesting to find out. It would take a different experiment, though.
One last question, yes.
Thank you. Thank you very much for the nice talk. I wonder what is exactly the relationship between the soil type and the grass type. And I mean, this is not a real question, because if there is like a cool relationship between these things, could we actually scale up this amazing thing and think about protecting the world from the dust storms in China? Can we actually plant this on the cluster too and stop the emission of the dust? And I actually do something very environmentally engineering thing and do something very good. Have you thought about this and about bringing this to the next level eventually? This would be fruitful.
Yeah. There are many different labs working on this around the world. There are people working on the Lus Plateau on similar work. I collaborate with some of them. And there are people working in other Chinese deserts growing different biocrust organisms at a fairly large scale. And my colleague at Arizona State University is also working on this with cyanobacteria. And we also have a dust problem in Arizona. So yes, and yes.
I wonder whether this is actually happening or things are not.
Thank you. So our next speaker is Tal Polak. If you've been in the first session and you feel like deja vu, it's the same Tal. So Tal is from the INPA, and the Israel Natural Parks Authority, and she'll talk to us about where am I?
In situ.
Yes, in situ soil bioremediation to counter oil spill in a hyper-arid nature reserve, Evrona.
Hi, thank you everybody. And thank you, Oded, for inviting me for this second talk as well. So I'm gonna talk about an event that I guess a lot of people in this auditorium knows about. So this is Evrona oil spill. Evrona oil spill happened in part of the nature reserve. And this is in the hyper-arid region, really close to Eilat in the south of Israel. We're talking about an average of approximately 20 millimeters of rain. And this area is so arid, it only received their water from annual floods. And because of that, we have this, I'll go there later. And in the southern Arava, we have this salt flats, which will drain the water, and Evrona is one of them. So although they say all the rivers go to the sea, so in the southern Arava, the rivers don't go to the sea, they go to the salt flat, and that creates a very rich environment for the desert habitat. And one of the reasons for that is you can see all these Vashilya groves, or if Erigona is here, acacia groves, so you won't be mad at me. And these are keystone species in the desert habitat, these trees, and they are creating a very vegetation-rich and a biodiversity hotspot in the desert. So in December 2014, the Trans-Israel pipeline erupted near Be'er, which is the village where I live. And if none of you saw this video before, it's really interesting. This is, I think, one of the first videos of a river of oil. So we hear one of the rangers talking to the manager. So this is all of it is oil. It just floods like water. So the ranger knew what he was talking about. So to those of you who don't speak Hebrew, his last word that all of this is going to go to Evrona. So he knew what's going to happen because the oil flooded through the dry riverbed into the braided river and into the Evrona salt flat. So in most cases where you get an oil spill or soil contamination, basically you just want to excavate all the soil out, take it off-site, and treat it there. However, the problem is because of and I think I don't have the picture there, but because of the braided river, which is a very, very shallow waterways, we were very concerned about extracting all the soil and actually creating erosion because of the following floods and changing the ecosystem completely because of our actions to excavate this oil out. So we did try and think about, okay, let's try and do some in situ soil bioremediation. But the problem is this is very difficult in a hyper-arid condition of the Arava Valley. So we were thinking maybe we shouldn't touch it. Maybe, oil is organic. Maybe it will be okay if we leave it in the soil. So while assessing the damage, one of the ranger actually found that there was an older oil spill. And going back to the records, they found that there was an even bigger oil spill in 1975. That's the blue below. And at the first look, it seemed okay. It seemed unchanged. So they started looking at it and actually found that in the older oil spill, there is no new acacia trees, meaning there were no acacia trees younger than 40 years old. And this led us to the thought that there might be a problem. Maybe the acacia won't be able to germinate. So it went further into some germination tests, and you can see it here that in the two controls you get acacia germination, but in both of the oil spill, even the one from 40 years ago, you don't get germination. And if we did get germination, it was very, the plants weren't well, okay? They were shorter, they had less root hairs, so they were defective, meaning that they won't be able to actually develop afterwards. So we understood we have to do something. And we started with the first aid. We said, okay, the oil in 1975, it was just there. It just spilled there, and it was in the summer, so it just became asphalt. So let's break up the soil. Let's start cultivation. Let's break up the soil. Let's get some air inside and maybe water if there will be floods. And this is the way we did it. Again, we wanted to protect those braided river, really, really shallow waterways. And this is people from Samar Kibbutz. They were very excited to do it. It was the middle of the summer, 50-degree heat, but they were really, really happy to do this work. And they done it like this, manually throughout the entire area. And then we started going into some bioremediation pilots. I'll go fast forward. We had several companies that did a small pilot. And then from those companies, we chose several that can apply to do an extended pilot. And the one that won the contract, if they succeeded at the extended pilot, they will get to treat the entire reserve. So Liquid Gas was the company that won the contract from their result and from their proposition. We done a pilot of 1 dunam in a part of the reserve. We did a lot of soil samples. The main problem is that we discovered that, I already went to that. We discovered that actually the soil wasn't homogeneous, meaning that if we'll dig here and then half a meter by next to it, we'll get a vastly different results in concentration of oil, meaning that we had to see what we can actually, how do we get enough power to actually know what we're doing, and that's why we had to use a lot of soil samples. I'll go into that statistic soon. But our aim was in this pilot to see if we can get to 70% reduction in the shallow layer of the soil after 90 days treatment. So one of the reasons was that we wanted to actually get to the fact that our treatment won't cause more harm. Our treatment won't cause more disturbance than needed and won't add more water than needed. So we use, like I said, we had a lot of variation. So we had 250 soil samples, and this is in just a small, the small 1 dunam pilot. But then it will be duplicated further on. So we use, like I said, 2 different depths, shallow between 0 and 10 centimeters, and deep between 20 and 40 centimeters in the soil layers. The oil didn't penetrate more than 50 centimeters. So this was good to get a lot of variation. So these were the pilot results. Hooray, we got over 70% reduction in the shallow layers. So we were really, really excited from this result. The deep layer didn't give us any result because there were a lot of zeros. But also look here, we had the histogram, and we can see that the pink one is before the treatment. You can see the bell shape. But then what we were looking for is this shift to the left, this shift towards the 0 from all the samples, meaning we had quite a reduction of the oil in the ground. We also did some germination tests. This is my result, but we've done it as well in the gene bank. But we can see that we had 2 control samples. So we had soil, which is control from other parts of the reserve. We had control that it's a clean soil that were treated with the different materials. And we had the oil that undergone treatment and cultivation. So we have germination there. This is also an amazing result over here. And we can see that any other, either soil or oil that was either cultivated or just treated without the cultivation didn't have any germination, meaning we have to have the cultivation and the treatment as well. So after the pilot success, we went to treat the entire nature reserve, which is, as you can see, quite a large area. And all of these are very, very narrow, very, very spreaded river with that we need to spread the entire irrigation system for the treatment throughout this area. This, again, was quite a difficult treatment, and it was on the skirt of COVID as well. So we had to do it with everything going on. This is, again, it finished around the end of March 2020. I remember because there was a big flood, and I went there, and I gave birth to my son on the same day. We went to see what happened to the irrigation system. After 3 months, we did another soil sampling, and you can see that the results were not duplicated in the upscaling. So while the pilot, you can see in the corner there, had over 70% reduction, the full treatment only had 32% reduction. And if we go back to that amazing histogram, it's not duplicated here as well. So bioremediation, where we used water and specific bacteria and other materials to reduce the oil in the soil, didn't work in the hypoarid zone. And it was less than 50%. And from our germination tests, we know that even 5% might be a problem, meaning that we haven't solved the issue in Hebron. I mean, we haven't restored the germination of the acacia trees, which was the main function that we were trying to install again. So because we failed in that and we weren't able to, so if we leave it like this, the ecosystem, it won't happen in our lifetime, but because these trees will live for hundreds of years, but in 100, 200 years, this ecosystem will start to degrade. The trees won't have new recruitment, and it will come less and less an acacia grove, and the ecosystem itself will just disappear. And this, like I said, this is a really important biodiversity hotspot in this region. So we understood that we still have to restore their ability to germinate. So our next step will be to replace the soil. We are going towards extracting the soil. Again, this is a very complicated situation. You can see how shallow the waterways are. We need to extract the soil very carefully so we won't cause soil erosion that will cause just 1 or 2 or 3 deep rivers, and we will lose this braided river. And from the entire time we dealt with this, we haven't found, and there was, I'm finishing, and there was a lot of literature surveys, we haven't found a similar situation where you have oil spill in a hyper-arid nature reserve that needed to be treated. You can have oil spills in the desert and nobody cares about them, like after the Gulf War, but here we do care, and this is, for us, one of the major places in the southern Arava to treat. So hopefully, if we do find a successful treatment and we will manage to restore the germination, it will be a good example for when we'll have other incidents, and they will happen. And this is my last note before the thanks, is that accidents happen. This was an accident. It might have been prevented, but it might have been less oil, but it was an accident. Nobody dumped it intentionally. But as we can see, restoration, especially in an area like this, is nearly impossible. And the amount of money, effort, and basically what will be left, because we won't be able to restore it 100%, is devastating. And I think this is the lesson we need to learn, that prevention is probably better than restoration. And I want to thank everybody here, including Kata, because they did assist us in a lot of the things that we needed, and all of these companies that were part of this mega project of restoration trial.
Thank you. We have time for questions.
That's it? Everybody is depressed enough?
Instead of trying to restore the whole area, why don't you create islands for where the trees can grow?
So the problem is, and this was brought up, and also was brought up by some experts, maybe we'll plant trees. And the problem is that acacia trees are so specific, and they, after a flood, you'll see a mat of seedlings, and then only maybe one of them will survive, because they need to find this microhabitat inside inside the braided river, maybe on the side where we'll get to the water that will be there in the dry season. And we don't know where that is. We aren't able to create those conditions. To my knowledge, there hasn't been any successful planting of an acacia trees that didn't need to be irrigated throughout its life. And again, this is a nature reserve. We want it to be sustainable by itself. We don't want to keep on treating it as a garden. This is a nature reserve that needs to be self-sustained.
More questions? Can you tell us,
The method that you use to contain the soil?
This is their liquid gas trademark. I don't remember the entire details. I can say it was involved 2 materials, one that actually broke the carbon chains a bit, and then another material that kind of conditioned the soil and made it softer and helped the water with the bacteria to go in. And then you had the bacteria, which were brought from overseas and they were capsulated, and they need to go through a jacuzzi process where they are in warm water and being massaged and kind of treated nicely, and then put into the soil via the irrigation system. So, and that's the process, and then they kept on receiving water for 3 months, and then after 3 weeks, they got another bacteria induced because the first batch got in, their explanation, they got in too fat and lazy and start capsulating again, so they needed a boost with new bacteria, but that was the process.
More questions? I have a few, but I'll ask one. I changed one right now. You did a lot of irrigation as part of the organization process. Did you see any effects outside the river bank of 3 months of irrigation in a hyper-arid area?
One summer, it was our, it was our concern. We didn't want to bring invasive weeds, they did have some, problems with foxes coming in, biting the pipes, but they solved that quite easily. But the main issue is that once it stopped, and this is the reason we wanted it to be very, 3 months and not 12 months and not 14 months, because we wanted to reduce the damage we will do with this cleaning process. So once it became summer, everything just gone. So nothing survived in the desert without water. And this is again the answer for why can't we plant acacia or do islands of clean area, because we don't know where it's going to be. The underground flow is different than what we see, so we don't know where will be the best place to put them. And this is part of the hardship.
Thank you very much. So our next speaker, maybe less depressing.
Yeah, this is what I was saying.
So our next speaker is Merav Seifan, and I decided that the closer you are to geographically here, the longer your affiliation will be. So Merav is from the Mediterranean Department of Desert Ecology here in the desert. In the Jacob Blauschen Institutes for Desert Research. She's also the head of the Albert Katz School for Desert Studies.
International.
Oh, you say it was too short, sorry. And she'll talk to us about the combined effects of large herbivores and arid conditions on the composition of desert vegetation.
Also, the title is long, so. Okay, so.
And I read only part of it.
Yeah, okay, so as Oded said, it will be slightly less depressing, at least, I think. And I think that we can start by having a few working assumptions. And the main one is that when we are looking at plant communities in arid areas like our desert, we can assume that there are a lot of limiting factors that are affecting what we see and what the species can actually survive in this area. And therefore, everything that we see locally, we may assume that they are already, or the species that we see co-occurring together are those that already are adapted to the specific condition. And when we are looking at a specific patch and we are looking at a local community, then the individuals, the origin of the individuals is either those that are already growing there, those if they are long-lived, they will already be there, or they are the source that were produced as seed that were locally dispersed in this specific area, or they were brought there as seeds from other areas. And eventually all those seeds and all those plants are being the thing that dictate eventually what we will see in the area will be affected by two main things. We can divide it into two main things. First of all is the abiotic conditions that are there, and we are talking locally in this area. So when we are talking about desert, we are mainly talking about water availability, soil structure, things like that. And we have also the interaction with I don't know what to use, so I'll use that. And we are also looking at the biotic interaction, and since this is what I promised in the title, we are mainly going to look at large herbivores and their effect. And since we're talking about plants and plant abscissas, we also have the leisure. What do I need to do? Apparently there are some instructions there, so I don't know, to talk a little bit, well, God. Okay, thanks. Usually I'm screaming so much that nobody needs that, but okay, fair enough. So what I wanted to say is that eventually, because we're talking about sessile organisms that are there, we also have the leisure to decide on which part of the life history we want to talk. And in this case, we can either talk about the above ground vegetation, what we see what we see that is growing there, or we can also look and focus on the seed bank. And the advantage of looking at the seed bank is the fact that we basically have the potential to see what is the vegetation that can potentially grow in this specific area, and not necessarily looking at what can grow in this specific season that we happen to be in the field and look at the things. So this is what we did in this case, and since we are talking about the Negev Desert, I want to introduce you to the Negev Desert slightly. So this is our area. This is the highlands of the Negev Desert. It's a hyper-arid area. It's mainly limited by water, and the one thing which is very useful in the Negev is the fact that we have a very clear strata in our landscape, and topography is a main issue here. So we have those wadis, we have the valleys, and where most of the water and the organic matter is accumulating. And this is usually where you found most of the vegetation. And we have the ridge and the slopes where other things also can grow. And we have our herbivore, and luckily I had also the leisure of not explaining too much about the herbivore, because Shirley Bar-David have already done it in the morning. So we are talking about the wild ass. And the Asiatic wild ass, I just want to remind you, it's a large equine herbivore that was native to this area, was completely extinct somewhere, I think in the 50s. I'm sorry if I'm not completely precise here, but it was reintroduced by the Israeli Nature and Park authorities in the 80s back to the area. So now it's back there. And this is our large herbivore. And since we are talking about a vulnerable species that is of high interest to the conservation in this area, it's also being monitored quite largely and basically also managed. And when the one thing that is being managed in this case is the fact that we provide water to those animals. Again, Shirley already explained about it in the morning, but the main problem that we have in those areas is that since humans have captured most of the water in these areas, we need to provide back somehow. And this is being done by artificial water supply to those animals. And specifically in the area of the Negev Highlands, historically there was one water hole that provide and supply water to these animals. But this is very useful for people like me who are plant ecologists, because the fact that we have animals, large herbivores, that have affiliation now to one artificial water hole. Of course, it's not the only resource for water for them, but it's a major source for water for those animals. We can assume that most of those animals need to go back to this specific area once every 3-4 days to drink. And therefore, because they have this spatial dependency on the water hole, there will be an uneven distribution of the animals around the area. And therefore, we can also assume or have the hypothesis that there will be a change in the effect of those herbivores on the landscape in which they actually being active. And from that, we can derive maybe the hypothesis that there will be a differential effect of the wild ass in the area in relation to how far away we are looking from this historic water hole. So this is what we wanted to check. And as I said, I want to start by looking at the long-term effect, and this is why we were focusing on the seed bank sampling. The water hole is here, up here, and what we did was to have samples that will be distributed spatially all over the geographical unit that represents the Negev Highland. I want to say that here we have the Ramon crater, and here we have another geological unit. So we basically spread all our samples in the Negev Highlands. We try to distribute the samples in a way that we will actually cover everything there, topography, different geology, and different distances from the water hole. We basically have 149 sites that we sampled. In each of the sites, we sampled around 10 liters of soil. So we basically took the Negev Highlands and brought it here to the net house and just saw what we have there. We let it germinate. We let those 10 liters of soil from all the different sites to germinate in a net house for 3 years, because we also wanted to overcome dormancy to make sure that we are really seeing what's potentially in each of those samples. And eventually, just to give you another spoiler, eventually what we found was 148 species of plants in all the different samples. And the major question that we have, as I remind you, is basically whether we can see some connection between the wild ass presence and the composition of the vegetation as it reflects in the seed bank. So this is our question. We want to see this connection between the wild ass and the seed diversity that we see locally in each of those samples. I want to remind you that basically, since we are talking about the long-term effect, we are going to use the distance from the water hole as a proxy for the intensity of the presence of the wild ass. And since we know it's the Negev Desert, and I've already said that it's not the only thing, certainly not the only thing that dictates what you can find germinating and growing in each of this area. Whoops. We also added some other factors into the story. First of all, geographic location, basically the spatial location and the elevation of each of the samples. And second, this topography thing. In topography, I mean whether it was the sample that came from a ridge, slope, or different parts of the wadi, from the smaller wadis to those large wadis where when you imagine those large floods in the desert, this is where they go, okay? So we had those topography. As you already saw, we analyzed this data, this specific thing we analyzed. We started by looking at the diversity per se. And diversity we analyzed using structural equation models. I'm not going to go into all that. If you want to ask about this, I'll be happy to explain more later. I want to focus on two different things here. First of all, this very, very sad error here, which is basically what I wanted to say. And this is the effect of our proxy of wildlife potential, the effect of the wild ass on the seed diversity, and the fact that there was no significant effect of the wild ass present on the seed diversity. And this is in relation, if you compare it, for example, to the effect of topography here, you see that this is a very fat error here, which basically represents the fact that there was a strong topography effect on the diversity, the local seed bank diversity. It's not a huge surprise, but it's sometimes nice to have a little bit more look into something which is relatively trivial in order to reassure yourself that your model is right, and it's really, from that point of view, the distance from the water hole was not significant. So I want to go in small detail into this topography stuff, just to give you a hint of that. So first of all, as we said, the general diversity of the seed bank, local seed banks, in relation to topography. So we start from the ridge, slope, and then different order of wadis, so increase in those runnels. And first of all, what I want to show you that overall, the diversity of seed bank, you don't see a lot of trends here. But if you are now focusing on different subsets of the seeds, and especially comparing between annual richness of the annual plants, that the seed that we see there, and the perennials, then you start to see things that you are very familiar to anybody who's hiking around in those areas. So first of all, for example, when you're looking at the annual richness of the area, again, in relation to topography, then we see something which is very familiar, that we have an increase in the diversity of annual plants, of annual species, when you're going from the ridge to the small runnels, not in the large wadis where there's too much flooding going on, and there you don't find a lot of annuals, but you see this nice increase. And this is in comparison to what you see, for example, in relation to the diversity of perennials, where you mainly see less perennials on the top of the ridge. This is where there is more erosion, it's a more exposed area, so this is when you're looking with your eyes, you see that there are less perennials there. Okay, so this is quite trivial, but it gives us some reassurance that our analysis was correct. You can then say, okay, it's not about diversity, it's about species composition, right? So this is what we did next. We looked at the species composition. In this case, we were focusing on the beta diversity, so the turnover, the change in species composition between to every pair of samples, so every 2 samples that we take, and what is the change in the identity of the species that we find there. We focused again on the differences in the position, in where each of those samples were in relation to the water hole. This was the major question that we asked. But again, we know it's not the only thing that is affecting the story here. So we added also the geographic location under the assumption that closer points will have, of course, more similar species in them. And we also add topography because we saw topography definitely is affecting what you find in the desert. So again, we analyze this using generalized similarity models. I'm not going to go into the details, but I want to emphasize 3 things here. First of all, the model itself was pretty weak. So most of the variance in the diversity of seed bank diversity was not explained by this model. But if anything did explain the diversity, this was topography again. Okay? So very similar results. Just to give you some visual hint of what we see here. So this is just a visualization of what we saw before. So you are probably familiar with those kind of graphs. The closer to each of the points here represent different sites. We have the 148 sites. The closer they are, the more similar they are in the species composition. And the major thing that I want to show here is the colors represent the different topography. And what you can mainly see here that the sites that are more connected, the sample that were taken on the ridge and the slope are more similar in their species composition than those that are from the wadis themselves. Okay, and the computer is telling us something, so. Not now, okay. So this is the topography, again, nothing interesting. I want to just to convince you that this is the story because I want now to show you what happens when we are putting the distance from the water hole. So again, this is the species. We eventually want to look at species, right? So, sorry. So just to give you what were the major dominant species that were affecting this whole analysis. So again, this is species that you will find immediately when you go to the field. So erodium species, we have this Artemisia that is very common on the slopes and on the ridge of the area. This is in comparison to what you find more into the floods area. Again, things that everybody is hiking around in spring will know. So we have this Anthemis. We have a lot of different grass species in the area, like this Schismus, the Arbormus, Brachypodium, all sorts of things that are here. This is, as I said, in comparison to if I'm taking the same analysis and just put the visualization in relation to what is happening in relation to distance from the water hole. So this is exactly the same thing. Just now, each of the colors represent distances from the water hole. And here, you can see that it's a mess. So there is no direct connection between the two things. This is, I want to say, even though when we are looking at the dominant species that are helping the statistical analysis to separate between or showing what is the differences between the different samples, we do find species that are known to be associated with with herbivory, especially these two. It's just 2 examples, this Spergularia species and this Malva species. They are known to be associated with herbivores. And still, if you can see, you can see if I will be able to manage this thing. They are actually situated in 2 different parts of the analysis. So it's not about that. So if I just want to sum up what we found till now is that the seed bank composition is highly diverse. This is maybe not surprise. And it's probably mainly affected by very local habitat conditions. And from conservation point of view, which is why we are gathered here today, the major thing that we found is that there is no clear effect of wild ass presence on the seed bank. I want to say as reflected in distance from the water holes, which may represent or suggest that our vegetation and our plant community in our area is actually pretty resilient to the effect or the presence of the wildlife, at least potentially. Now, I want to say 2 things about this conclusion. First of all, it may well be that distance from water hole is not necessarily the most relevant variable to explain the effect of wild ass. It may be. But I want also to say that when we are looking at the above ground vegetation, we do see that there is a very strong effect of the wild ass, and around the historic water hole, there is basically nothing left. So it seems that there is an effect. We are investigating it now, but at least we don't see it in the potential seed bank or not, at least not seeing it yet in the potential seed bank. This is the first thing. The second thing that can also be is that basically we have the wilderness in the area for so long that they already kind of homogenize the whole area and just we don't see the effect anymore. Very well, I cannot overrule that at all because there is no way to analyze that. I can only say that since we find 148 species in the seed bank, and this is all the usual suspect, including very rare species, including very interesting and the thing that you would expect to find in our area from historical time and from all sorts of lists that we had around, it seems that at least potentially this vegetation, the community of the Negev highlands is pretty much intact, at least for now. And with that, I want to finish, and I want to say thank you to all the brave people who actually did all the work, and of course for all the sponsors that we had. And thank you for listening.
Thank you. So we have time for about 2 questions, and for those who are asking, please speak loudly or get a microphone. Or bring it. Yes.
Is there any evidence of wind blown dispersion of seeds?
Evidence, it's difficult, but we know from the, okay, sorry, I still need to do that. Okay, so I'm not sure about evidence, but we know that we have species here that are dispersed by wind. We have a lot of grasses that are dispersed by wind, we have others, so it's part of the community. So
no wind pattern effect.
you mean that there is that you would expect there would be a directional dispersal in the whole Negev highland? Yeah, no. I don't think that. I think that the micro climate and the wind direction is so local in this area. We know it also from the rain and stuff that I would be surprised, but.
Thank you for this wonderful talk, really inspiring. I was wondering, can you assume that these assets move in a direct line from the waterhole to away, or are they sometimes collared, or some of them collared, so that you know where they actually move, and then maybe that might be the clue later that they're not going directly far and from, but move in certain areas, and then if you know that, then you might get a better idea.
Okay, so first of all, we don't assume it's a direct thing. It wasn't an assumption here. We also, by the way, in the models, we tried all kind of different non-linear thingy to make sure that we are not just assuming a linear effect of distance from the waterhole. This is the first thing. Second, yes, there are, and Shirley, she's not here, but they and Amos Buskila and others have looked at the color movement of the species. There are models for that, not necessarily for especially this area. It's something that we can use, but overall, again, because the animals they're definitely roaming the whole area. So we were more looking at it as a probability of meeting a wild ass in different areas. And that's it, nothing more. I cannot say anything more than that. I want to add to that now part of the monitoring that we do also on the above ground vegetation, we also put a few, not enough maybe, but a trail camera. And one of the things that we are trying to do is to have an additional kind of assessment of the activity of the animals in relation to where our monitoring samples are located to have a better assessment. But since we're talking about the long term here, and this is for I don't know for how long, 40, how many years is this waterhole there? 30 years? 20? Yeah, so we took it as this is the only real stuff that we have there, that we know that they are coming. If you look at the area, you see they are there. So this was the assumption here.
Thank you very much. Okay. Our next speaker will be Yaron Ziv, and Yaron Ziv is from Ben-Gurion University and starting a trend of having heads of school giving talks in this session. Yaron is the head of the School of Sustainability and Climate Change in Berger-Tal University, and he'll talk to us about studying restoration-oriented mining of phosphate in the Negev Desert. Yaron, thank you.
Thank you, Oded, and thank you for the opportunity, and thank you for coming. Actually, it's quite late already. And I would like to describe a little bit our study on restoration-oriented mining of phosphate in the Negev Desert. There are many collaborators, and we are going to see more names in a few slides. But I would like actually to mention Nathan Levy. And you see Nathan Levy here in the picture. Nathan was a PhD student of Tarin Paskagan, Arnon Carnielli, and myself. And he went to travel in India 2 months ago, and he was found dead in his hotel room. A wonderful person, very friendly, great job he did on remote sensing, and we miss him. So I would like to dedicate this talk to Nathan. I would like to mention that originally I was planned to be the first presenter, so there are some facts about restoration, definitions, and so on. I think it's interesting, so I'll keep mentioning what I wrote. So, of course, many environments are severely degraded, so the ecological needs, both abiotic and biotic, for the organisms are absent, and if we want really to recover a system, we have to do something about it. Mostly actively, and this is what restoration is all about. As you know, restoration, the concept of restoration has many definitions. This is one of the common ones. So the restoration, the process of assisting the recovery of different levels of organizations. I won't read anything, but this all is a means of conserving or enhancing biodiversity and ecosystem resilience. And I think that we all understand, and we'll do it more often actually in the future, that ecological restoration is a major pillar of conservation biology and must receive special consideration by government, organization, and academia. And as I just mentioned that, I would like to mention a few facts about restoration worldwide. And I took this information from this documentation that just came in April 2022 by the UNCCD, and I also actually cite some of the Baron, are you here? He's somewhere around in this conference, but he also gave a talk in the Ecology Restoration Society Europe 2 months ago, so I'm actually taking some of the information from him. So over 40%, if not 70%, if we take into account all the indirect effects of ice-free terrestrial ecosystem have been transformed from their natural state for human use. And this is huge, and we see all the impact and all the consequences of that. 1 in 5 of those hectares or these areas actually is no longer productive. We're talking about 20%, which is really, really used, undermining the well-being of 3.2 billion people in the world. We are lucky, we live in the OECD and rich countries, most of us, and we don't influenced by that, but many people in the world are influenced by habitat degradation and so on. And without significant change, i.e. a business as usual, a further degradation of 16 million kilometers square is expected by 2050, which is the size of South America. And we keep doing the same thing, and unfortunately, this is where we are going. This means that about $44 trillion is at risk by the current degradation. And again, it has consequences for our future existence. Interestingly, when we talk about restoration and recovering of the system, economic returns of restoring land and reducing degradation, greenhouse gases emissions, and biodiversity loss are estimated at, well, I can't realize these numbers, $125 to $140 trillion per year, which is 1.5 times the global growth domestic production in 2021. It's huge. And something which is really cool, I think, and some recent studies by the EU show that for €1 invested in restoration, about 8 to 38 euros are gained. So this is not only just, this ecologist crazy dreams about recovering biodiversity, it definitely has economic values and social values, and there are actually new books about the social value of restoration. So it becomes definitely a major topic in world sustainability that takes into account, the economy, the society, environment together. And it is not surprising, I guess, that the UN declared this decade as the ecosystem restoration decade. Something very interesting, and we might want to be aware of that because it comes with resources and new calls and new opportunities in the next few years. The EU just came with a proposal just recently, and we're waiting to see what the Council will decide about the nature restoration law. The idea is to restore land and sea area by 20% by 2030 and 59% by 2050. And this comes with legal acts, support, subsidies, sanctions, a lot of resources. Basically, on a nation basis, each country in the EU is supposed to come with decisions what and where to restore, how to finance restoration, how will it link to other land and sea use, public stakeholder participation, and so participation. There is no rainfall of stakeholder. And this can be definitely available for us too, collaborating with European countries. And they're actually going from about 20 billion euro a year now invested in restoration and recovering degraded areas, all the way in several years to 100 billion euro a year for restoration. So they really take it seriously. So what I would like to do is just to say a few words and to describe our system of the restoration-oriented mining of phosphate at Yaron Ziv area, Negev Desert, that we work for about 6 years. And there are, again, as I said, many collaborators. Some of the people that actually are here with us, some of them no longer work in the lab, and a lot of collaborators like Eli Saadi, who is here, and other people that I see. And I'm going to mention some of the work we have done in the last several years. So in general, we're talking about that phosphate is mined in the Negev for more than 70 years. Actually, it started as a governmental company. It was successful for several years, but later on it wasn't very successful. And in 1991, the company, the phosphate mine company, was purchased by the Ofer family, and it is now a private property, or not property, private industry. It is an open pit mining that requires the removal of soil and rock, and you see these huge areas to the right, really, really huge areas, and areas like that are very, very challenging in terms of restoration and recovering the original ecosystem. So you can understand that it's not an easy game here. The past restoration focused on landscape restoration, more kind of visual, not ecological one. So they used to take all these huge piles, put it in one place, and then start, reshaping the landscape so it will look nice. However, in the last 18 years, the new practice, which is the restoration-oriented mining practice, started taking place, actually, with a lot of modern encouragement by kind of enforcement by the Nature and Park Authority, the Ministry of Energy and Infrastructure, the Ministry of Environmental Protection, and this is definitely much better, where they take, and I'm going to show you that in a second, they're taking the topsoil and other layers and reshape it, keeping the original watershed structure. So we were asked, as I said before, 6 or 7 years ago, by the company to evaluate how successful is this practice. And with our collaborators, we have 2 major goals, really major ones, kind of umbrella goals. One is to evaluate how well the restoration practice recovers the abiotic and biotic factors, conditions. and to suggest additional practices to improve restoration, and we do a lot of work with this respect. Just to show you how this restoration-oriented mining practice works. So if this is like the potential area for mining, so the company divide the area into strips. They go for the first one, they harvest, they take the highest, the upper level, which is the topsoil from their respect. It is not really our biological topsoil. It's not the 5 centimeters or between 50 to 80 centimeters, but they pile it in a designated area. Then they take the overburden, and then they take out and mine the phosphate. Then they start with a second strip and fill in the first one, and so on. And when they get to the third one, the third strip, they actually take the topsoil and cover the first strip, and that's how they move step by step. And basically, at the end, everything is supposed to be restored with the topsoil above in the original watershed structure, in order to keep the landscape like it was in terms of the rivers, the valleys, and so on. So what we did after a while, after a few actually years that we started realizing and understanding the system with a lot of readings, we constructed an entity relationship process-based model where we actually identified physical states, functional states, and biotic states. And actually you see that the soil crust is both in the functional and the biotic state. And you can understand why, and we'll talk about it later. But basically, we identified the specific, this is a minimal picture, by the way. We could add many more parameters or variables into this model, but we really wanted to keep it simple. But as you see, it is not simple at all. We identified each of these paths with the negative and positive feedbacks, and by doing that, we were able actually to provide, this provides information on the mechanistic relationships between the biotic and abiotic factors, so it helped us to understand what is going on, again, with reading and references and all the information that we gathered about on this system. Then when we have something like that, you can focus on limiting factors and bottlenecks. So this definitely directed us to specific goals and targets, because you cannot explore everything, you cannot experiment with everything. You really must understand where you want to go with the limited time and the limited resources that you have. So that's what you have, and definitely something that I always recommend when you do restoration is to have some mechanistic model that will enlighten and give you where to go, and you can always go back and see if you did the right thing. I hope we are doing the right thing. We use an ecosystem approach with a food web perspective, so we work on and we look at soil, and we'll mention it with physical, chemical, and biological properties, and we also assisted with Eli Saadi on that, microbial community, plants, and arthropods. And we use, again, I'm going to really give you a few kind of, just the flavor of what we do, because we don't have time, but basically we use diverse methods with field surveys, geoanalysis, genetic analysis, lab experiment, greenhouse experiments, which I'm going to show a little bit, field experiments, short and long irrigation system that we have in the field for 4 years already, and remote sensing hyperspectral. This is what Nathan was studying. We have a protocol-based research system, and we have basically 4 sites of restoration: Gov, Chagor, Afik, and Saif. And the year next to the name of the site is the year of restoration. So you can see that Gov is the oldest one, so something like 15 years already since restoration, and Saif is the youngest one, about 7 years from restoration, and each site with its, with its identical monitoring and material collection design. I'll go very fast. just about the findings, and I'll show you some examples with the soil. This is, again, Nathan Levy's work, and it was published already. We had this hyperspectral flight and image, and with the soil properties, Nathan was able actually to create a soil type mapping, and we see that different soil types at different mining area. So we start with differences at the beginning when we just compare between the different sites. There is a huge variation in all soil properties at both restored and natural plots, really huge. We always sometimes we look at the desert and we think, oh, this is a very homogeneous environment. It is very heterogeneous, probably much more than many other ecosystems worldwide, and so there is huge variation. But when we looked at the differences between the restored and natural plots in the different properties, we saw that it was significant. It is significant, the difference between the biological properties. The other ones were not found to be significant. When we talk about a microbial community, this is the work of Talia Gabay, and we compare between the restored and natural plots, we see that they differ very significantly in microbial diversity. Post-mining means restored, undisturbed mean natural, and you see that in each of these sites, these are different microbial communities entirely. So they are not similar at all. Some of the research sites differ in microbial diversity. In other words, within the restored sites, even if we take out the natural ones, the restored sites differ among each other, and that actually suggests that what we saw about the different soil types, really these things talk to each other. And the most important one, we have many other results, but just I think the important one is that the most important order, the cyanobacteria, is mainly missing from the restored plots, and you see it very clearly here. And we know that cyanobacteria, which is mentioned a lot here throughout the last 2 days or 3 days, this one, the ecosystem engineer, is really missing from the restored site, regardless if it's GOV, the oldest restoration site, or the youngest one. With respect to vegetation, this is the work of Tom Zilberberg. Tom, you can raise your hand, okay? In the field, when Tom looked at restored and natural plots, they differ in plant species richness, except for a GOV site, and you can see that in this cluster analysis to the right, GOV plots are actually nested within some of the natural plots. In the greenhouse, a lot of work that Tom did, the restored and natural plots differ in germination. So we took soils from the different areas, natural and restored one, put in the greenhouse, and we let them with irrigation and water and good conditions to germinate. And except for GOV, you see that there is, and just ignore the treatments, just look at the orange and green dots, regardless of the symbols, just because we don't have time to get to each of the treatments. Basically, except of one plot, some samples in the GOV site, the species, the germination, the community according to the germination experiment are different between the restored and the natural plots. And something which is really interesting, what Tom did, we bought seeds from the seed bank in Volcani Center, in the center. We bought seeds, and we brought into the greenhouse soils from the restored natural plots and different sites, and we just distributed, we germinated these seeds, okay? And we found that there is no, we didn't find any significant effect in germination between the different soils. And that suggests that it is not the quality of the soil itself. This is because seed bank is the limiting factor for species diversity in this area. And this has the reason we think this exists is because we don't have the cyanobacteria in the soil crust to allow these seeds to settle down and to germinate. Just the last ones, in terms of arthropods, restored and natural plots do not differ in arthropod species diversity, but abundance is higher in the restored plots. The restored and natural plots show different community composition, and you see this, the MDS similarity or dissimilarity graph, and you see that each of these sites is somehow nested in a different location, so they're really different than each other. The interesting thing, and this what gives us the result or explanation why we saw abundance more in the restored one, because in the restored plots, we found very generalist and opportunistic species. So basically ants and some very generalist beetles were found in the restored ones, and the total abundance was higher. However, if you look at the specialist species, the more specific ones are significantly more abundant in the natural plots. So just to summarize, different sites are different in their soil types and physical conditions, which make our life much more difficult. So we can't just go to one site and understand how to do that. We have to look at each site specifically. Another disappointment was that time since restoration, succession trajectory cannot explain differences between sites, because we really hope that if we have different years from restoration, we'll be able to get a trajectory and then infer about the processes and maybe use it for restoration for the entire area. No, again, each site has its own attributes, own personality. Restored areas do not represent the natural areas yet, unless we wait 1,000 years. I don't know how many years we need to wait. They are dissimilar in their biological properties, with some deficiency in soil organic matters and other soil properties. In other words, restoration is not there yet. There is still a lot of way to go in order to have good restoration. Flaty habitats seem to recover faster, makes sense, and it has to do probably with geomorphologic stability, and we studied that, and definitely additional active practices are required, and we do, again, a lot of experiments and studies now to see how we can actually do it better. I'll just skip this one and tell you that the last one is that now we're actually working with a company, and the idea is to create huge, large-scale modules of much higher heterogeneous habitats with some what we call eco-elements with trees, water, sink, and boulders in order to increase species diversity and maybe create these islands of cyanobacteria and other materials that will be able somehow to expand to the entire environment and speed up the recovery of the system. And I'll stop here. Thank you very much. Good one.
Any? I can. Yes. I was wondering if this might be related to what Tal presented about. What sort of regulations are there for liability or restoration, remediation by private enterprises to restore the environment?
What, by the company?
Yes.
The regulation, the kind of the law?
Yeah.
Wow, it's a good question. It's a very good question. I think that I'm very embarrassed as a citizen in Israel. This specific area, we have the new Oron Sin program, Oron Sin HaChadasha, which is quite impressing in a way of what the company has to do. However, and they need to do, and there is a team with the people from the National Park Authority, and they're involved in that, and things are kind of moving. But in terms of regulation, we do not have regulation, restoration regulation in Israel, like the American law, and I really hope that things will be somehow changed. Maybe we can do something about it, but we need a law for restoration. We don't have it in Israel. So it's on a project basis, okay?
Thank you very much, Yaron. And the last talk of the session will be Ilan Stavi from the Dead Sea and Arava Science Center. And he'll talk to us about geodiversity enhances resilience of dryland ecosystems to climatic changes. Thank you.
So the good news that somehow I understood that I have 12 minutes, so it's going to be very short. So in this presentation, I'm going to show findings from 3 different projects, of which one has finished and 2 others are running. And as you can see here, there are many partners that have collaborated in this project. So geodiversity, it encompasses the natural range of physical components of the system. It affects biodiversity, ecosystem services, and in our terms specifically is hydrological connectivity. So the first topic to be discussed is geodiversity, its implications for dryland functioning. So the study was implemented in the Sayeret Shaked LTER Park, which is located in the semi-arid northwestern Negev. Now, the region has experienced over the long run precipitations reaching 250 millimeters annually. Now, during the last 2 decades, precipitation has decreased to 150 millimeters only, and simultaneously with that, a mass mortality of shrubs has been observed with a particular impact on the Nuea mucronata, which you can see its pictures over there. So over the last 2 decades, the mass mortality of shrubs has been extensively studied, but almost without referring the physical background. And as we can see here, this is a long-term precipitation regime across the region. So we can see not only many drought years, but also sequences of droughts. And this is how the Nuea mucronata dead shrub looks like. Now, when we arrived to the field site, we quite immediately, we found that the mass mortality of shrubs is confined to a type of a hill slope like that in the left side, which we characterized as homogeneous hill slopes. While in heterogeneous hill slopes, in the right side, this mass mortality of shrubs was not observed. And this is how the systems looks like in the winter or in the spring, with homogeneous hill slopes to the top left and heterogeneous hill slopes to the bottom right. And here again, to the left side, homogeneous hill slope, where we can see there is no rock fragment cover, and the soil is deep and non-stony. While in the heterogeneous hill slopes to the right, there's a substantial rock fragment cover, and the soil is very shallow and stony and overlays fractured bedrock. And this is the mapping of the 2 hill slope types, with heterogeneous hill slopes to the left, where we can see 6 shrub species, or dominant shrub species, which altogether cover about 25% of the ground surface, and most of the individuals are alive. While in the homogeneous hill slopes to the right, only 2 shrub species, dominant shrub species, which together cover about 7% of the ground surface, and most of the individuals are dead. And this is the results of GPR, Ground Penetration Radar, down to 0.4 meters. So in the top, we see a homogeneous, the subsurface of a homogeneous hill slope, while in the bottom, we see the heterogeneous hill slope, where we can very easily notice the irregularity of the underground of the subsurface of the heterogeneous hill slope. And this is the GPR results for a deeper depth of down to 1.4 meter. So on the top, homogeneous hill slope, on the bottom, heterogeneous hill slope, for which also here we can easily notice the irregularity of the subsurface. And this allowed us to draw this characteristic pedon for a homogeneous hill slope in the upper right, and a heterogeneous hill slope to the lower left. And to some extent, this may explain us why the shrubs do not survive in the homogeneous hill slope, where there is a competition with the herbaceous vegetation throughout the soil profile, while in the heterogeneous hill slope, only the shrubs can penetrate through the cracks in the fractured bedrock. To some extent, as I said, it's not the entire explanation. And this is the soil water index, as wrote 5 years between 2013 and 2018. So as we can see here, the soil water index is consistently greater in the heterogeneous hill slopes in blue than that in the homogeneous hill slope in red. Now the differences between the two hill slopes types is substantially prominent for severe dry years, as marked here with A, B, C, where we can see that the soil water index is much greater in the heterogeneous hill slopes in red than that in the homogeneous hill slopes in blue. And this is a mathematical modeling of shrubby vegetation dynamics under decrease in precipitation. So we see from left to right, when precipitation decreases from 1.5 millimeter a day down to 0.9 millimeter a day. So in the homogeneous hill slopes, in the upper row, we see that the shrubby vegetation decreases and then totally collapses. While in the heterogeneous hill slopes, to the bottom, to the lower row, the shrubby vegetation decreases but does not collapses. Now, what happens if precipitation decreases and then increases back to normal? So, in the homogeneous hill slope, in the top, the shrubby vegetation decreases, collapses, and does not recover. While in the heterogeneous hill slopes, to the bottom, the shrubby vegetation decreases and then increases back to normal. And here we see the effect of precipitation decrease from right to left on shrubby vegetation. So we can see that when precipitation decreases, the first system to collapse is homogeneous hill slopes in black. While in heterogeneous systems, they do collapse, but only later on. Whereas the greater is the heterogeneity, the later on is the ecosystem collapse. So far for the first case, and now we'll move to the second case of geodiversity in rangelands, for which I will very shortly present some preliminary results. So the concept of this project is to assess the ungulate roots' impact on geodiversity and specifically the implications for geoecosystem functioning. So the study is currently being implemented along an aridity gradient from north to south with a dry subhumid region, semi-arid region, arid region, and hyper-arid region. And here we see the livestock trampling roots marked with 1, 2, 3, and 4, and their effect on the hill slope incline here. So as we can see, the incline of the roots is much smaller than that of the rest of the hill slopes, and this is expected to have implications for the hill slope profile and hydrological connectivity. And here we see the effect of precipitation decrease on shrubby vegetation in systems with trampling roots in red. So as we can see, the shrubby vegetation in these systems decreases but does not collapse, while in system without trampling roots, in blue, the shrubby vegetation decreases and then totally collapses. And also here we see where precipitation decreases from right to left and how it affects the shrubby vegetation. So also here the first two collapse are the systems without trampling roots in black, while in systems with trampling roots, as we see in red and blue, they do collapse, but only later on. And to the topic of human-made geodiversity, for which I will also present very shortly some preliminary results. So this is a bilateral project between China and Israel as partners. So in the Chinese side, the Chinese are aimed at assessing two ecological restoration case studies. One is ant forest in the top two pictures, and the second is straw checkboards in the lower pictures. So unfortunately for these two case studies, I don't have preliminary results to present, but for the Israeli side, we also have two case studies. One is afforestation, specifically for the contour bench terrace system of the KKL, which you have seen during this conference. And specifically here, what we see is the land use change, meaning the transformation of natural land into lands into afforestation land, and how it affects the NDVI. Now, since the tree cover, even in the most old systems, is rather low, then we assume that the entire NDVI is related to herbaceous vegetation. So what we can see here is that in the relatively old systems, in the top of which were established in 2005 and 2009, the herbaceous vegetation increases following land use change, while in the relatively recently established system, like this one, which was established in 2016, the herbaceous vegetation decreases following land use change. And this fits well with previous studies of us in the very same forest, the ambassador's forest. And to the second case study here in Israel, we assess the ancient run of harvesting systems, which are dated to the late Islamic and Ottoman periods. So practically, we simulate the effect of ancient stone terraces on hydrographs and accumulated runoff volume. So generally, what we see in all these graphs is that the terraces lower the hydrograph and decrease runoff loss, and a greater terrace effect in high-frequency storms than that in low-frequency storms. Thank you very much.
Thank you. Questions? So, and the
first part of your presentation, you were talking about homogeneous versus heterogeneous plots, and in the heterogeneous part, you mentioned faunal perturbations. Were they rodents digging underground, or what were the faunal perturbations?
If rodents can...
No. You said that in the heterogeneous plots, there was a lot of faunal perturbation. Were they rodents, or what type of faunal perturbation was it?
Well, I did not mention any perturbation, but rather the let's call it the soil profile in the homogeneous is pure soil. We were interested to know what is the soil depth in these two hill slope types. So we took like a 1 meter long piece of metal, and we pushed it into the soil by hammering it into the soil. So in the homogeneous hill slopes, this piece of metal ended without reaching the bedrock, okay? While in the heterogeneous sill slopes, we dug about 10 centimeters and we reached this bedrock, which was highly fractured. And also these 10 centimeters in the heterogeneous sill slopes were highly stony, like about 30% of volume is rock fragments. And in addition to that, significant rock fragment cover on the ground surface. So this makes the difference between the two systems.
More questions? Okay, so I want to thank all the speakers of this session and Ilan. Thank you.